Alright, so we'll make a series of videos here on exponential functions. Let's start by comparing them with something we're very familiar with, x squared. It's a parabola. It's the simplest parabola. Let's try plotting these and see how they compare. Now x squared, when x is 0, x squared is 0. And when x is 1, x squared is 1. When x is 2, it's 2 squared. It's 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared, gosh, I don't know what 6 squared is. Oh, it's 36. That's not very hard. I was thinking of 16. And then so on and so forth. We could even do up to 49 here. So this is a parabola. Right? It grows pretty quickly. Right? A lot of upward motion without a lot of side-side. Now what about 2 to the x? Alright, so 2 to the x. When x is 0, 2 to the 0 is 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth power is 16. So let's start sketching these in. Right. And then 2 to the fifth power is 32. And then 2 to the sixth power is 64. So however fast we think that x squared increases, 2 to the x increases much quicker. Right? Faster. Now we can actually quantify this using calculus. So you might have learned about something called L'Hopital's rule, and if you haven't, you will. I'll move this down a little bit. And it's a way of comparing how fast functions grow. And we can actually use a limit for this. And we kind of view this like a race. Alright, so we can take a ratio as x goes to infinity and see who wins. Now 2 to the x, it looks like it's growing faster than x squared. Who gets there first? Now right now this is an indeterminate form. It looks like infinity over infinity. Now we can't say anything about that necessarily. It's not necessarily 1, it's not necessarily infinity, it's not 0, it's not 5. It's indeterminate. We have to do more work. What L'Hopital's rule says is that this limit can be redone. So this limit is equivalent to the ratio of derivatives. Now why is that? Well, here's one intuition. Suppose these both indicate position. Maybe these describe the position of two people having a race as a function of time, where x is time. So we're running along. Somebody has a position which is 2 to the x seconds, or x squared seconds. How far are you from 0? Well, you just plug in the time. So we know they both go to infinity if we wait forever. Right? So wait forever. But that doesn't really tell us much. So what we could do instead is we could look at their velocities. All right. Well, the derivative of 2 to the x is natural log of 2 to the x. More on that later if you want to see it. And the derivative of x squared is 2x. So these might represent their velocities or speeds. Being a little sloppy with the difference. Now, unfortunately, this is still 0 over 0, as x goes to infinity, 2 to the x goes to infinity, and so does 2x. So, what can we say here? Well, if you wait forever, they get arbitrarily far away. And if you wait forever, their speeds are arbitrarily high. Alright, so that doesn't tell us anything. Well, we could look at their accelerations. This is just using L'Hopital's rule again. So let me just indicate here. The idea is to look at the derivatives to compute the original limit. So these are kind of like speeds. What about accelerations? So again, we take a pair of derivatives. ln2 is just a constant. And we're going to pick up another ln of 2 when we differentiate the 2 to the x again. And then we'll just have a 2 in the bottom. So these are like accelerations. Well, finally, we're getting somewhere. This limit just goes to infinity because the 2 doesn't do anything. So how can we interpret this? We can say that if somebody's position is an exponential function, if we wait forever, they become arbitrarily far away. If we wait forever, their speed becomes infinite. But also, if we wait forever, their acceleration becomes infinite also. Now, what about the bottom? What if somebody's position is determined by x squared? Well, if we wait forever, they're arbitrarily far away. If we wait forever, their speed is arbitrarily large. If we wait forever, well, they have a constant acceleration. So it does take them forever to have an infinite speed. This, the fellow in the numerator, their speed is increasing much faster. So if you can picture this as a couple of people, running, all right? This is my running. The 2 to the x fellow, their speed ends up, their acceleration is larger than this person here, and so their speed increases more quickly, so they pull ahead, right? Starting both at 0, 0, the 2 to the x person gets to infinity first. This is how we can evaluate this. As an aside, if you take the limit of the reciprocal, whoops, not e, 2 to the x, x goes to infinity, this would be 0. The idea of this is that this limit of derivative over derivative is equal to this limit of derivative over derivative, which is equal to the original derivative. And the punchline of this is that exponential growth is really fast. All right, I'll make a different video about another property.